We've seen how to do configurations for atoms, which are electrically neutral. How do we do configurations for ions? Well, what we're going to do is add or take away electrons from the valence shell of a configuration to get ion configurations. There's a three-step process for doing this. Step one, write the configuration for the atom. Step two, put it in shell order. Now remember, there were two different orders. There's the fill order for the subshells, and then there's shell order, which is ordered by the n quantum number, the shell number. And we'll see how to do that in a minute. Add or take away electrons from the right side of the configuration. And I mean right as opposed to left. So let's suppose we've got this ion. And I want to write a configuration for it. Let's follow these steps. Step one, we have to write the atom's configuration. So I'm going to look for indium, that's IN. There it is. Okay, if I want to do the configuration, I am going to need to first find the core. So here, indium's core is krypton. That's the end of the previous row. Now I'm going to count on top of the krypton core. So here's krypton. I go down to this row. I've got rubidium, strontium. What am I counting into there? Well, we're in the S block, and we're in 1, 2, 3, 4, row 5. 5s1, 5s2. Let me write that down. Okay, so I've counted 5s2 in here. What are these? Well, these are 3Ds, so these are 4Ds. So if I'm confusing you here, you go back and do lesson 3.5, because we did all this back then. These are the 4Ds. 4D 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4D10. And then there's indium. What am I filling in with that last electron? Well, we're in row 5, right? 1, 2, 3, 4, 5. And we're in the P block. So this is a 5P. This is 5P1. So there's my configuration for indium. Now I'm going to put it in shell order, which just means jumbling the shells around so that they go in numerical order. The 4 has to go before the 5. So I'm going to put this in front. Now why do I put it in shell order? Because when I'm making ions, all the action is going to happen in this rightmost subshell first. And then if I need to, I'm going to go to the next subshell in. And if I need to, I'll go to the next subshell in. So you work from the right and then work inward. Now, I have to take away one electron because I've got a positive charge. If there's a positive charge, if it was a +2, I'd be taking away 2. What if it was a minus? Then I'd be adding an electron. If it was -2, I'd be adding 2 electrons. So I got to take away 1 electron from this configuration, and I'm going to work from the right. There's 1 electron in the 5p subshell, so I'll be rid of that. And so my final ion configuration is going to be that's it. I took away that 5p1. This is the configuration for the indium 1 ion. You can say the indium plus 1. Now, let's go a different way. If I look at the shell order, I can see that this is going to form a plus 1 ion because the highest subshell is being graded here. It's being electrons are being taken out of it. And the highest subshell is going to be the one on the right. So a positive ion forms when the highest subshell empties, or when the highest shell, the valence shell, so what other ions can indium form? Here's indium, the atom. I could take away 1 and that would empty out the highest subshell. If I took away 1 electron, I would predict that would give me indium with a plus 1 charge. If I emptied out the highest shell, how many electrons am I taking away? 1, 2, 3. So I'd be emptying out the 5th shell. And then I'd have, this is indium plus 1. I could have indium plus 3. So in other words, I've used the electron configuration for the atom to predict the 2 most common ions of indium that form. Let's do another one like that. Let's do tin. Okay, well, tin, we're going to write down the electron configuration for the atom. Let's see, tin has got a krypton core. And I'm counting over here, again, 5s, whoops, you can't see that. 5s1, 5s2, because I'm in the 5th row in the s block. 5s1, 5s2. 4d10. And now I'm in the 5p's. 5p1, 5p2. Put it in shell order. Okay, now I want to predict the ions that tin, Sn, is going to form. What do you think? You can form ions by emptying the highest subshell. And if I do that, the highest subshell is the 5p. So if I empty that out, I'm going to have tin with a plus 2 charge because I'm taking away 2 electrons. And the electron configuration for this tin 2 ion is going to look like this. And I could also empty the highest shell to form an ion, a positive ion. So if I do that, I'm going to take away all the things that start with 5. I'm going to take away 4 electrons. And then what do I have? A 10 plus 4 ion. So I have predicted from the electron configuration that these are the 2 most common ions of tin, and that happens to be the case in real life. Now what about negative ions? What do you do with those? Well, with negative ions, they are going to be even easier because they try to get a stable configuration by grabbing electrons from something else. Nonmetals do this. Nonmetals form negative ions, metals form positive ions. So, if I look at fluorine, it wants to pick up enough electrons so that it is like the nearest noble gas. There is something about the noble gases that makes them very stable chemically. We've already said that they're noble gases because they don't associate with any of the other elements. They don't form compounds. They don't even react with themselves. They're monatomic gases. So there's something especially stable about their electron configuration, and if other elements can get a noble gas configuration, then they are going to be especially stable too. So look at fluorine. It's got 9 electrons. If it can pick up 1 more electron, it can have a neon configuration. And I could write very quickly the configuration for a fluoride ion, F- ion. It wants to be like neon. It has just a neon configuration. It's just the core. What about oxygen? Oxygen wants to pick up 2 more electrons to be like neon. It has a neon configuration. What about arsenic? What kind of ion is it going to form? Well, this is really a metalloid, but it's going to act just like a nonmetal. So when I say nonmetals form negative ions, metalloids do usually too. So the arsenic can go and do 1, 2, 3 electrons. If it picks up 3 electrons, it'll have a krypton configuration. So the most common ion, negative ion of arsenic that I would expect would have the same configuration as krypton. So doing negative ions is pretty easy. Doing positive ions, you have to go through that 3-step process that we did before. We're going to look at this process of getting a stable noble gas configuration in a little bit more detail in the next video.